All right, so in this chapter we've been talking about how we can add things across carbon-carbon double bonds, right? What drives those reactions to completion? What drove this reaction all the way to completion? This reaction will go to completion. If I have enough mercury around, it'll go to completion. Why?
Because the product has a lower energy than the reaction.
True. And why? Why is the product lower in energy than the reactants? That's right. We've broken a weak pi bond and gained two strong sigma bonds. That's right. And so that determines why these reactions are said to go to completion. It's all about the thermodynamics. Okay? And so we've learned that we can add a variety of things across the carbon-carbon double bond. We can add halogen, right? We can add chlorine and bromine. Iodine we can't. Well, it adds, but it reverts, right? And fluorine goes boom. So for all practical purposes, we're stuck with bromine and chlorine, right? For all practical purposes. And we're going to end up with what's known as a vicinal dihalide. Vicinal meaning that the halogens are on adjacent carbons. Okay? We learned last time in the inverted lecture, what's the stereochemistry of a vicinal dihalide? So we add the X's on the same side or on opposite sides? Why is it opposite?
Because the way that it's not a carbocation, but it has a sort of intermediate that forms.
Okay, and what do we call that? What do we call that sort of intermediate? Bridged halonium ion. That's right. So we form a three-membered ring with the halogen. And the way that this reaction occurs is that as the pi bond is reacting at the halogen and kicking out the other halogen as a halide, the lone pairs of electrons on the halogen that's being attacked come back and react with the other carbon. It's a concerted process. And so the first halogen is added only on one face of the alkene. And it has to be that way because a three-membered ring defines a plane, or 3 points define a plane, if you will, right? And so would you predict this to be stable or highly reactive? And why? Ring strain. What else? You think halogens like to be positively charged? No. So it's got ring strain, which is the big contributor, and of course the fact that you've got a positively charged halogen in the mix. And so now the halide that functioned as a leaving group in this first slow step can now function as a nucleophile and attack one of the carbons. In this case, the carbons are equivalent, so it doesn't matter which one it attacks. But this is kind of like what? What other reaction does this kind of look like? It looks like an SN2. The nucleophile is attacking from back, and the leaving group is leaving, 180 degrees, if you will, or pretty close to 180 degrees, right? The only difference here is that this leaving group is attached to another carbon, and so it can't completely leave, right? But the fact that we go through a three-membered ring and that the halogen has to come in from the backside is going to guarantee that these halogens are added in an anti-fashion. And in fact, that's what we see exclusively in these reactions. Okay? So for example, how do we know that this is the case? We know by looking at stereochemistry. So all that stuff that you learned in chapter 5 is important here. So if we take cis-2-butene and trans-2-butene in separate flasks and brominate them, we will actually end up with different products. If you take cis-2-butene and you react it with bromine, you end up with a pair of enantiomers. These dibromoethane molecules are actually enantiomers. How will I get them? Racemic or one enantiomer over the other? Racemic. But they are enantiomers nonetheless. You get a 50-50 mix. However, if I take trans-2-butene and do the same chemistry, I don't end up with a pair of enantiomers. I end up with a meso compound, which is achiral. So how are these products related to these products? They are isomers. Are they constitutional isomers? They have the same connectivity, right? Do they not have the same connectivity? So what are they? They are diastereomers. And so these enantiomers in this meso compound will have different what? Will they have the same physical properties or different physical properties? They'll have different physical properties because they're diastereomers. These molecules will have different melting and boiling points than these, and so we can actually use their physical property differences to determine that this reaction actually occurred the way that it did. Your take-home assignment from this slide for Wednesday is to prove that cis-2-butene must give a pair of enantiomers and trans-2-butene must give a meso compound. Bring that to class written. Use your model kits. This is known as a stereospecific reaction. If we start off with cis-2-butene, we get enantiomers, and that's what we get. We don't get any of the meso compound. If we start off with trans-2-butene, however, we only end up with the meso compound, not a pair of enantiomers. So I want you to put together a rationale for why that's the case, mechanistically. So you need to make your argument based on mechanistic considerations. Okay. Now, sometimes we do these reactions in the presence of water. So when we take an alkene and a halogen, it can either be chlorine or bromine, and we have water around, we don't end up with a vicinal dihalide. We end up with what's known as a halohydrin. Can anybody tell me why we end up with a different product? Pardon? There's a huge amount of water, that's right, and it's going to function as the nucleophile. You're still going to go through that bridged halonium intermediate, but in the presence of water, you got a ton of water, right? I've asked this question of you multiple times. Approximately, what's the concentration of pure water? It's about 55 molar. That's right. That's a lot, right? Go home and try to make a 55 molar salt solution. You can't do it. Won't get that much in. But water's extremely concentrated. And so when we have the bridged intermediate, of course we have the halogen that can function as a nucleophile, but you've got, let's assume it's 1 molar halide, okay? You have 55 times as much water. So which one wins the nucleophilic race? Water, because this is like an SN2 reaction, right? And so the rate of this reaction is going to be dependent on the concentration of this times the concentration of water, right? The rate of reaction of this attacking this is going to be dependent on the rate of these, or on the concentration of these two species. This just wins out because you got a lot more water around, okay? And so the final product is going to be syn or anti-addition. It is anti. So you're going to end up with an alcohol on one carbon and a halogen on the other. And when we have that in a vicinal arrangement, we call them halohydrins, okay? And these are important intermediates in organic synthesis. We use them all the time to make a variety of molecules, okay? However, has anybody ever seen bromine? What's the physical state of bromine? Is it a solid, a liquid, or a gas? It's a liquid, but it's a very volatile liquid. You can come down to my lab. I've got a big bottle of bromine, and if you open the bottle up, immediately this red gas starts coming out of the bottle. You think that's healthy to breathe? No, not at all. It's pretty difficult to work with sometimes. How about chlorine? What's its physical state? It is a gas. Chemists typically don't like working with gases. You have to have a lot of tubing, you have to have regulators, you have to have safety valves. We like working with liquids and solids. But bromine is pretty volatile, and so it's a liquid. It can be worked with, but it's not one of those liquids that you can work out on the normal bench. You got to be in a hood to work with it, okay? However, we can use this molecule. It's known as N-bromosuccinimide, and it's just abbreviated as NBS. you can think of it as a solid equivalent of bromine. Okay? NBS is a nice white crystalline solid. I can go to the bench where my scale is. I can weigh it out. All I need to have are my safety glasses on and my gloves. I don't have to wear a respirator. I can just weigh it out very, very easily. And what NBS does, when you place it into water, it slowly decomposes into bromine. So it's a nice, convenient source of bromine. Now, what we typically do when we're trying to make a halohydrin with bromine, instead of using bromine and water, we'll use NBS, we'll use dimethyl sulfoxide, and we'll use water. What's the purpose of the DMSO? That's exactly right. It's to dissolve the NBS in the water. Okay? And, of course, the alkene. Okay? But anytime you see NBS, DMSO, and water, you need to think of bromine and water. That's how it behaves. It behaves as bromine and water. Okay? And so it's a nice, convenient reagent. And it allows us to do these bromohydrin formations very, very easily. Okay? So, for example, if we take cyclopentene, bromine and water, we end up with a pair of enantiomers. And notice we end up with the anti-configuration, the OH coming out of the plane or behind the plane, however the case may be, and the bromine the opposite, right? So here the bromine is coming towards us, the OH is going away, and exactly the opposite here. These are a pair of enantiomers, and so we end up with this bromohydrin, as we call it, okay? Now we notice here that the carbons of the alkene are identical, right? So does it matter which carbon the water attacks? No. But down here, are the carbons of the alkene identical? No. And so what happens is we could have the possibility of the bromine being on this carbon and the OH on this carbon, or vice versa, right? We only get this product. Why do we only get that product? And why is the water going to attack the most substituted carbon? Because of what? You're right. Let's go a little deeper, though. Why does it attack that carbon? What's the intermediate that we're going to get? What are we going to get, Nathan? What's the intermediate going to be when the halogen reacts with the alkene? The very first intermediate. How? Yeah, we got a bridge species, right? And one of these bonds is longer than the other, right? And you're right, because this is positive, it's going to try to pull electrons to itself. And the best way to do that is between the most substituted carbon, that bond, right? Because that'll put a partial positive charge on that carbon as it's pulling the electrons to itself. So that weakens that bond. And that's how we end up with the product that we see there. Okay? So is that a Markovnikov addition or an anti-Markovnikov addition? It's Markovnikov addition. Why is it Markovnikov addition? Because the OH is on the most substituted carbon. The electrophile is on the least substituted carbon. Right? This is where my electrophile is going. That's the bromine. And my OH, the nucleophile, is going to the most substituted carbon. That's exactly like a Markovnikov addition. Except we're not dealing with hydrogen as the electrophile, right? We're dealing with bromine. And so that's the big difference there. But it's all about that weak bond. Even though we don't have a carbocation, which is really what Markovnikov's rule is about, we do have something that's starting to resemble a carbocation. And so we see that we end up with the OH on the most substituted carbon and the bromine on the least substituted carbon. Okay? Just talked about that. Now here's why it's important. you can take this alkene, and we would predict that the halogen will go here, and the OH will go here, following what we just talked about, right? And in doing so, we get this halohydrin. So what must the reagents have been to make this? Water and chloride? Chlorine, that's right. So they use chlorine gas. Okay, so they'll take this, they'll place it in water, usually with a co-solvent, so that everything dissolves. And then you bubble chlorine through it, and you'll end up with this halohydrin. Now, what's kind of cute about these halohydrins and where they come really, really useful is you can treat these things with base, and you get epoxides very, very easily. You have all the chemistry knowledge you need to tell me how this happens. How is that second step happening? Pardon? Repeat that? What hydrogen?
The one that's on the OH.
Ah, because that's the acidic hydrogen, right? And so what do we get from that? Right? Now what happens? What happens?
Electron pairs go with one of the hydrogens on chlorine.
Close. What do we have to do? What bond do we have to make? What bond do we have to break to get the product? Pardon? I have to break the carbon-chlorine bond, and I have to form what bond? A carbon-oxygen bond. So what do I need to do? Show me how to push the electrons. And I end up with the epoxide. That's nothing more than an internal Williamson ether synthesis. Alkoxides plus alkyl halides give me what? SN2 reaction we talked about in the previous chapter. An alkoxide plus an alkyl halide gives me an ether. What's an epoxide? It's an ether. It's a special ether because it's a cyclic ether. It's a strained ether, but it's nothing more than an ether. Okay? And if we look at this, because this is added in a trans fashion, right, the oxygen is going to be on the opposite side. So once we form the alkoxide, it can come in directly from the back and kick out the leaving group. Okay? And it works really, really well. So these halohydrins are quite frequently used to make epoxides. They are not the only way to make epoxides, but they are an excellent way to make epoxides. Okay? And then in one step, they took this molecule and made estrone, okay, which is a sex hormone. Okay? So using sophomore level organic chemistry, you can make these complicated medicinally active compounds, okay? Or medically active compounds, I should say. Okay? So halohydrins are useful. That's kind of the take-home message here. Now, wait a second. Hold it. I thought OH, though, and alcohols, they have about the same pKa, right? So am I going to generate a lot of the alkoxide? No. So why does this go to completion then? I'm not using an extraordinarily strong base, right? So I'm not generating 100% of the alkoxide, so why does the reaction go to completion? I'm talking about B to C. B to C goes to completion. But I'm not using a strong base. I don't completely deprotonate the alcohol. I don't have 100% of the alcohol as the alkoxide when I add sodium hydroxide. So why does the reaction go to completion? A little principle you learned about in general chemistry. Sounds very French. Pardon? Le Chatelier's principle. That's exactly right. So we're not going to generate 100% of the alkoxide, but as it reacts, what happens to equilibrium? It gets shifted. That's exactly right. So even though we only generate maybe less than 1% of the alkoxide with sodium hydroxide, it will react and form the epoxide. Once we have that, that shifts the equilibrium and we generate more alkoxide, and it just continues to react. Okay? And so don't forget about good old Le Chatelier. Okay? Comes in handy. Let's do a quick concepts test. I want you to give me the products of these reactions. Green and yellow. Walk me through the first level of knowledge. What is the product going to be? How would you name the product? Not the IUPAC name, but what kind of functional group are we going to get? A bromohydrin. On an exam, knowing just that level of information, you can eliminate some answers, right? You know that NBS, DMSO, and water is going to give you a bromohydrin. So anything that's not a bromohydrin can't be the answer, right? The second thing you need to know, right, is that NBS, DMSO, and water, we can really think of that as just simply bromine and water, right? So that'll help simplify life for us. Now all you have to decide is which carbon gets the bromine, which carbon gets the OH. Which?
Bromine is the electrophile, because you said it last time. It goes on the most substituted one, like with the most H's, right?
It goes on the one with the most H's, which is the least substituted. Close. Is there any stereochemistry that I have to be concerned with? It is going to be racemic. I do have one stereocenter, right? But do I have two stereocenters? No. So I don't have to draw them as being trans to one another because there's free rotation around this carbon-carbon single bond, right? So yes, I end up with a chiral center and I end up with a racemic mixture, but I do not have to show wedges and dashes because I don't have two stereocenters. So I don't have to worry about the relative stereochemistry. Now for the yellow one, chlorine and water, what's the product I'm going to get? That first level.
We're gonna have one chloride and one hydroxide.
Yeah, so we're going to end up with a chlorohydrin. And again, on any exam, anything that ain't a chlorohydrin ain't the answer, right? So we know we're going to end up with a chlorohydrin. Does it matter, in this case, which carbon gets the chlorine and which carbon gets the OH? Because they're identical, so it doesn't matter. However, do I have to show stereochemistry? That's right. And I have the option, right, OH and Cl. You need to show that the OH and the Cl are anti to one another, or trans to one another. All right? Am I going to get this as a single enantiomer or a pair of enantiomers? And what's the ratio going to be? 50-50, so it's going to be racemic. So I would just draw that and then write racemic. Because this is a stereocenter, and that is a chiral center, right? It'll always be anti because we're going through the three-membered halonium ion, in this case the chloronium ion, and then the water has to come in from the back. So as I drew it, the chloronium ion was formed on the opposite side of the board, and the water came in from this side and opened that ring. Now you could have drawn it exactly the opposite, and that would have been fine. Okay, it just would have been the enantiomer. Yeah. You now have enough tools in your toolbox that you can actually build some pretty complicated molecules, relatively speaking. You don't have enough tools, you have to go work for Pfizer or Merck, all right? But you got enough tools to do some things that I've never taught you before. So if we look up here, starting off with cyclohexanol, how would you end up with 1,2-dibromocyclohexane? Have I ever taught you how to take an alcohol and make a vicinal dihalide? No, I have never taught you how to do that. Yet you have every tool in your toolbox to do that. You just have to start getting creative. This is where we start to learn to think backwards. Not backwards thinking, but thinking backwards. And this is very, very important for those of you who want to go on to medical school, because it's exactly how you're going to think when a patient comes into your office. They come to you sick, and you got to work backwards to what the cause of that illness might be, right? What I want is 1,2-dibromocyclohexane. And we got to figure out, going backwards, how I can get that from cyclohexanol. Because that's all I got in my lab. I've got cyclohexanol, and I want 1,2-dibromocyclohexane. So we're going to start off doing what's called a retrosynthetic analysis. You start with the product, and you work your way backwards to the starting material you want, or that you have. So we know the product that we want is dibromocyclohexane. Now, a retrosynthetic arrow is a double-headed arrow like this, or a double, whatever you want to call it. It's this, all right? Basically, what it's asking is, or stating in this, is what starting material would I need to do this? I would definitely need bromine, and what else? And I would need an alkene. Very good. Do I have an alkene as my starting material? No. So I've got to go back at least one more step, right? How can I make alkenes? By dehydration of alcohols. That's exactly right. So now I've gotten to the starting material that I have. Now I do the forward synthesis. The retrosynthesis is theoretical. You don't have to have the exact reagents to do it. You just think logically about how you could do it, okay? So now going in the forward direction, what would I do to make the cyclohexene? What do I need for that? Sulfuric acid will work just fine. So you start off with your cyclohexanol, you treat it with sulfuric acid. What other acids could work in place of that? Sulfuric is a perfectly fine one, but what if you didn't have it in the lab? What else could you use? Phosphoric acid, and there was a third one I told you I was going to hold you responsible for. Para-toluene sulfonic acid, PTSOH. Any of those will work. Are there others? Sure, right? Those are the ones that I want you to remember. Sulfuric acid, phosphoric acid, para-toluene sulfonic. So now I've got the alkene that I want. Now how do I get to my product? If I use Br2 in water, would I end up with the vicinal dihalide? I would end up with the halohydrin, right? Now if that's what I wanted, that's what I would do. But what do I need here? Technically, NBS will work, but we haven't talked about that. NBS in water is what will typically give you the alcohol, or the bromine. What do I need here? It's just real simple. I just need bromine, right? And a solvent that doesn't react. Usually methylene chloride is what we use. Carbon tetrachloride, something like that. But that's it. But have I ever taught you how to go straight from here to here? No. And in fact, there is no way to go straight from there to there. But using a couple of steps and some creative juices, you can get from one place to the other very, very easily. Okay? Organic chemistry is not only a science, but a lot of people do consider it to be an art. Because there's more than one way to get here, actually. Alcohol is one way. If you had the alkene, that's another. And there's actually several other starting materials that we could use. What other starting material might we use to go from here to here? An alkyne. So, in theory, you're right, but what's the problem with that alkyne? A lot of strain. So that's not gonna work. What else could I do? What other functional group? Let's say Nick comes into my lab and he goes, Dr. Masterson, you don't have any cyclohexanol, but you have cyclohexyl chloride. Could I use that? Yeah. And how? How do I do that? How would I get to that? Elimination of what? Of the X and what else? And an H. So it's a dehydrohalogenation. So what reagent would I need? What would Danielle have to give me to do that elimination? What do you think, Katie? If I'm eliminating HX, what do I need as the reagent?
That one's the one that requires plastic.
If I'm eliminating a strong acid, what do I need? I need a base. Yeah. What base could I use? I could use potassium terbutoxide. I could use what else? That's kind of the go-to for me. What else? In theory, I could use OH, hydroxide. It's got some issues. It can also function as a nucleophile. What else could I use? DMSO isn't a base. It's a solvent. DBU or DBN. There's a lot of DBs. Yeah. But I can get there, right? So again, this is retrosynthetic analysis. It's how we start with a product that we know we want, and we want to get back to a starting material that we have ready access to. So medicinal chemists do this all the time. You have a biologist at Merck or Pfizer that identifies a molecule that has medicinal properties. Biologists don't know how to synthesize huge molecules, so they call on the chemist, and they say, we found this molecule in nature. It seems to cure cancer. But the problem is that the tree that makes this, to treat a person, would have to wipe out the forest. So we've got to find a way to make it in the laboratory. And this is a true story, actually. It's called Taxol, right? So the chemist then goes in and they figure out how to take that product and work their way backwards to starting materials that they have ready and plenty access to, right? So they start off with this big, complicated molecule, and they go one step back. And then they go back another step until they finally get to a starting material that they think that they can reasonably use and get started. And then they start thinking about the forward synthesis. So it is an exercise in logic, okay? And it's a very, for many of us, it's very fun. Some of you might not find it so fun. But it is nonetheless a valuable tool to have, whether you end up being a chemist or not. Because when you are a physician, you're going to have to be thinking this way. Why is my patient sick? Well, they got a fever. A lot of things cause a fever. Well, they got a fever and they're sweating, right? So you can work your way back to what is probably the root cause of their illness. This is why we say that doctors practice medicine. Because your diagnosis is really a hypothesis, and you're testing it by treating that patient. Okay? It is the scientific method. I don't care what the doctors say. It is. Okay? You are developing a hypothesis, and you're testing it by giving that patient some medicine. Does it always work? No, because you got it wrong, right? And that's why it's called practicing. All right.